Okay, so now we're going to talk about the regioselectivity and the stereoselectivity in the E1 reaction and plus the mechanism. Okay, you can go read about this, but I don't really care right now. So I want you to look at this reaction. We're going to draw the mechanism and talk about the regioselectivity and the stereoselectivity as we go by. Don't worry about it. All right, let's take a look at this one. So this reaction, you're going to see this reaction in the next chapter as well. All right, let's just show you at the beginning right here. This is an acid catalyzed dehydration. Dehydration means remove water. We are removing an OH, that's an alcohol, plus one hydrogen to form the beta hydrogen to form double bond right here. Basically, we're removing water. All right. So, and we use acid, which is sulfuric acid in this case, as a catalyst. All right. All right. Before we draw anything, you should realize that an OH is a good or bad leaving group. Oh, that's one of the worst, right? So we have the worst leaving group right here. It's not going to leave unless we make it a better leaving group. Okay, we're going to make it a better leaving group by using an acid right there. All right, so we're going to protonate it. One thing you should know, this solution contains a lot of water. It's an aqueous solution, right? And we have concentrated sulfuric acid into this water. Sulfuric acid and water, well, sulfuric acid is going to donate, it's an acid, right? Donates a proton to water to form hydronium ion. Basically, this solution is full with not sulfuric acid. Sulfuric acid dissociate, not sulfuric acid in here. Most of sulfuric acid is a strong acid, dissociate 100%. Remember that? So most sulfuric acid is going to be in the form of hydronium ion. So that's the reason why I use hydronium ion right here. No sulfuric acid floating around, they dissociate. Okay? All right, so protonation. All right, so that's a better leaving group now. If you remember hydronium ion, look just like hydronium ion. That oxygen with 3 bonds. Oxygen with 3 bonds. This guy is a real good leaving group. All right, so pK negative 1.7. All right, so it's going to leave to form a carbocation. And then you can do whatever you want right here. You can do E1, you can do SN1 in here. But this one, we heat it up. So the reaction is going to favor an E1 product. Okay, so find beta hydrogen. All right, this is alpha position. There are 3 beta carbon here, but these two are the same. These two are the same, and there's another one. So there are 2 types of beta hydrogen you can work with. All right, first type down here, elimination, you get that product. And the other type, so hydrogen at the top, or you can use this hydrogen right here as well. Do elimination, you get another one. Another one. DJ Colin. All right, so you get 2 types of products there. All right, so who's the side safe product? The more substitute alkene, this guy right here, that's the major product. All right, and as you see the overall reaction, we have this guy, 90% of this guy, and only 10% of that. Okay, so there's an acid catalyzed dehydration. First step is protonation, and then the rest is the same thing, carbocation formation. And then either you get carbocation, you can get either do nucleophilic attack to make an SN1, or you can do elimination right here, beta elimination to get to an E1 process. Okay, all right. Similar to an E2, right? Stereoselectivity. So an elimination favors trans over than cis. Over cis, right? Trans is more stable. Okay, and rearrangement. So what's our rearrangement? Remember that when you draw the carbocation, there are 2 events you have to keep in mind. We have rearrangement and then racemization, right? But this one, we don't do racemization here, no nucleophilic attack, so we can skip that. Just the rearrangement, watch out though. Look at right here. So we have acid catalyzed dehydration of this alcohol. Got double bond here, got double bond here, and got double bond there, all right? If you look at this, look at the structure of analyze the structure of the, not alkyl halide, the alcohol. This is gonna be a leaving group, right? The beta hydrogen is right here. We should be able to form just that double bond, not right here, not right here, but we observe it. See that? We observe right here, right? So there's a rearrangement in there. If you don't know what I'm talking about, don't worry. Let's draw together, right? This is an E1, or first step, carbocation formation, right? That should be the first step. But OH, the bad leaving group, you have to convert that to a better leaving group first. That's why we add a sulfuric acid right there, right? So sulfuric acid, basically a lot of proton floating around, hydronium ion protonation. You get that? All right, so this is a better leaving group now. So it leaves. What do you got? Secondary carbocation. Totally. That's highly possible that this guy will rearrange. All right, just go with the flow first. So beta hydrogen right there, alpha, beta right here. You can do elimination. You get the first product there, only 3%. Who cares? This is really, really minor. Doesn't matter. All right, make this carbocation is better. All right, so there's no hydride shift, so we have to do alkyl shift here. All right, alkyl shift. So you have the carbocation right there. Now this is your new alpha position. Your beta position, where they are 3 total, 1, 2, and 3. All right, 1, 2, and 3. These two are the same. So you just pick one of them and do. This one is different. All right. Do right here first. Do elimination. You should get that product, 64%. And you can do it right here. You get another one, 33%. All right. So every time when you see when you form a carbocation, when you draw mechanisms, you say a carbocation. Watch out for rearrangement, all right, and racemization only for the SN1 reaction, because that's nucleophilic attack from the front, from the back, top, bottom, depends on how you look at it. All right. Okay. All right. Let's summarize E1 and E2 real quick before we go.